First-order logic. In this section, we will discuss the nature of representation languages. Our discussion will motivate the development of first-order logic, a much more expressive language than the propositional logic. What programming languages lack is any general mechanism for deriving facts from other facts. Each update to a data structure is done by a domain-specific procedure whose details are derived by the programmer from his or her own knowledge of the domain. This procedural approach can be contrasted with the declarative nature of propositional logic, in which knowledge and inference are separate, and inference is entirely domain-independent. A second drawback of data structures in programs, and of databases for that matter, is the lack of any easy way to say, for example, there is a Pete in 2-2 or 3-1, or if the Wumpus is in 1-1, then he is not in 2-2. Programs can store a single value for each variable, and some systems allow the value to be unknown, but they lack the expressiveness required to handle partial information. For example, we're going to choose a way to represent a language, and it's going to be this. We know they are objects: cat, dog, house, John, and we know their relationships. So the cat has color, the dog has color, the house is bigger than, comes between 1, comes between 0 and 2. These are relations that relate the objects together more than two objects. And when they're facts, so which are one value for a given input. For example, X has a father, John has a father, it's a fact. John has head, it's a fact. John can swim, it's a fact. In fact, the truth value, true or false, I can say, for example, no one died yesterday, that's a fact. It can be false fact, but it's a fact. Another example is 1 plus 2 equals 3. The objects here are 1, 2, 3, 1 plus 2, and the relation here is equals and function is plus. 1 plus 2 is a name for the object that is obtained by applying the function plus to the objects 1 and 2. 3 is another name for this object. A square's neighboring, the Wumpus are smelly. Object, Wumpus and squares. Property, smelly. Relation is neighboring. A evil King John ruled England in 1200. Objects, John, England, 1200. Relation is ruled. Properties, evil king. A logic can also be characterized by its epistemological commitments, the possible states of knowledge that it allows with respect to each fact. In both propositional, the first-order logic, a sentence represents a fact, and the agent either believes the sentence to be true, believe it to be false, has no opinion. These logics, therefore, have these three possible states of knowledge regarding any sentence. Systems using probability logic, on the other hand, can have any degree of belief, ranging from 0, total disbelief, to 1, total belief. For example, a probabilistic Wumpus world agent might believe that the Wumpus is in 1-3 with probability 0.75. In a fuzzy logic, facts with degree of truth and known of interval value. Syntax and semantics of first-order logic. First, they have objects in them. The domain of the model is the set of objects it contains. These objects are sometimes called domain elements. Figure 8.2 show a model with 5 objects. Richard is his younger brother. John is a king, the left legs of Richard and John, and a crown. The objects in the model may be related in various ways. In the figure, John are brothers. Formally speaking, a relation is just a set of tuples of objects that are related. A tuple is a collection of objects arranged in a fixed order and is written with angle brackets surrounding the objects. Thus, the brotherhood relation in this model is a set. So we have a syntax to do. So this is the syntax of first-order logic with equality specified in Backus NOR form. The syntax is strict about parentheses. The comments about parentheses and operator precedence apply equally to first-order logic. Term. A term is a logical expression that refers to an object. Constant symbols are therefore terms, but it is not always convenient to have a distinct symbol to name every object. For example, in English, we might use the expression King John's left leg, rather than giving a name to his leg. This is what a function symbol are for. Instead of using a constant symbol, we use left leg John. Atomic sentences. Now that we have both terms for referring to objects and predicate symbols for referring to relations, we can put them together to make atomic sentences that state facts. An atomic sentence is formed from a predicate symbol followed by a parenthesized list of terms. For example, Richard is a brother of John. Richard and John are objects and brother is the relation. This states under the intended interpretation given earlier that Richard is a brother of King. Atomic sentence can have complex term as argument. Thus, Richard's father married John's mother. Again, under a suitable interpretation. Complex sentences. We can use logical connectives to construct more complex sentences. Just as in propositional calculus, the semantics of sentences formed with logical connectives is identical to that in the propositional case. For example, Richard's left leg is not a brother of John. Richard's brother is John. John is a brother of Richard. Richard is a king and John is a king. Richard is not a king, that implies John is a king. Quantifiers. First-order logic contains two standard quantifiers, called universal and existential. Universal quantification. This symbol is usually pronounced for all. Remember that the upside-down A stands for all. Thus, the sentence says, for all x, if x is a king, then x is a person. The symbol x is called a variable. By convention, variables are lowercase letters. A variable is a term all by itself, and as such can also serve as an argument of a function. For example, left leg x, a term with no variable, is called a ground term. Existential quantification. Ex is pronounced there exists an x such that, or for some x, intuitively, the sentence exp says that p is true for at least one object x. More precisely, exp is true in a given model under a given interpretation. If p is true in at least one extended interpretation that assigns x to a domain element. So you will read this as, there exists a country and C borders Spain and C borders Italy. Nested quantifiers. We will often want to express more complex sentences using multiple quantifiers. The simplest case is where the quantifiers are of the same type. For example, brothers are siblings can be written as ax, ay, brother, sibling, xy. Or for all object x and for all object y, if x is a brother of y, that implies x and y are siblings. Consecutive quantifiers for the same type can be written as one quantifier with several variables. For example, to say the siblinghood is a symmetric relationship, we can write for all object x and y, if x is a brother of y, that implies x and y are siblings. Connections between for all and there exist. The two quantifiers are equally intimately connected with each other through negation. Asserting that everyone dislikes parsnips is the same as asserting that there does not exist someone who likes them, and vice versa. We can go one step further. Everyone likes ice cream, means that there is no one who does not like ice cream. For example, for all object X, if X likes ice cream is equivalent to there does not exist if object X does not like ice cream. Equality. We can use the equality symbol to make statements to the effect the two terms refer to the same object. For example, John's father implies Henry, says that the object referred to by Father John and object referred to by Henry are the same, because an interpretation fixes the referent of any term. Determining the truth of any equality sentence is simply a matter of seeing that the referents of the two terms are the same object.